thanks everyone. Organizers first, and then you to stay here till late. Very last session of this wonderful workshop. Thank you very much for the organization. And I think, okay, this I think I give you asked for abstract 1 year ago, I think, or something. It's kind of, and then this is the title I put it. But you will see, I think it's quite. I can, in this talk, make a summary of almost all topics in this conference. The idea is, okay, first of all, the important people here, Tim sitting there. Yesterday he had a poster and a part of this talk. And Ilya Togati was in San Sebastian. Now Tim is in the Netherlands, but is kind of a PhD student of us. So, and the idea here is to show you that all these effects we have discussed today and also yesterday are related both to spintronics, which are the magnetoelectric effects, I will just explain you in an introduction, and this diode effect, finite junctions are kind of related if we look that in a scale of transport. And I emphasize that we are looking for transport properties, and for that we don't need to go to microscopic, but then we would like to have a theory built just on symmetry, and today we had a very good point. So let us follow the Landau school and try to build such a fundamental theory. Phenomenology is always very strong, as we know. We're still using Ginsburg-Landau to describe superconductors, even though we know that only phenomenology is there, but it's quite, it survives. So, and then I will try to be very brief in this part, which is the technical part, which is the work by Tim mainly, how to build this universal phenomenology, quantum kinetic theory, give you some examples, and try to convince you that all these things that or many of these topics that we discussed today, yesterday, are kind of connected. Okay, so magnetoelectric effects, let me just first mention the first one. Magnetoelectric effect we have seen, we are interested in transport, is the spin Hall effect. We have see examples of that, experimental examples, and this connect a charge current to a spin current. So, and if we go a bit mathematically, please don't be scared about indices here. This is a spin current because it has two indices, direction and polarization, and we want to connect it to a charge current, which is a vector, and this is what's called a second rank pseudotensor because it has two indices, and it behaves like a pseudotensor. So what we need here is a third rank, so we are just, these two indices has to be summed, so it remains this connection between these two guys. And for that, we have in 3-dimensional, this third rank pseudotensor, we can write it right away. For example, isotropic material, centrosymmetric, we can write the totally asymmetric tensor, epsilon ij, you know probably from the studies x, y, z, if they change two indices, it changes the sign. So it means that the spin Hall effect is something that you will find it in almost every material if the spin-orbit coupling, if you can couple spin-orbit coupling, sizable, no? Platinum, for example. Now there is another type of magnetoelectric effect, which is a bit more subtle, which is called the spin galvanic effect. And this effect actually was pretty much discussed in the literature. You connect a spin charge current with a spin density. And again, we do the same analysis. Here we have a charge current, which is a vector. Here we have a spin density, which is a pseudo-vector. So we need a second rank pseudotensor. And this is not very often found. In order to have a second rank pseudotensor, you need, per definition, those systems that had chirotropy. And we can get back to this concept of chirotropy here. So there are materials that allows for such a tensor, pseudotensor to exist, and these are chirotropic materials. Okay, so example, Rashba. We have seen today a Rashba system. In the Rashba system, we have a two-dimensional, usually two-dimensional electron gas. We have a polar axis, which is this n, and we contract this n vector with our totally asymmetric tensors. And here we are. Here we have our second rank pseudotensors. So if spin-orbit coupling is sizable in that system, we expect to have a spin galvanic effect. Okay, so and this is why, indeed, in that symmetry we have seen a wonderful experiments by Christoph in which they apply the magnetic field perpendicular to the current flow direction, and they obtain a beautiful diodes effect. And let me just now give you a picture of how it works. So in principle, we apply that field, and as I tell you, we have the spin galvanic effect, and then we should get a current. But the ground state of our superconductor doesn't can carry any current. So in that case, how we compensate that current that actually we obtain, and this is what in the previous talk was called the finite momentum Cooper pairs, or let me just put it the name here, helical superconductivity. So our order parameter has here now, you see a finite Q naught vector, and this will compensate these currents if you just think in terms of spin galvanic effect, but no current flow in our superconductor. That's prevented current to flow, so ground state is 0. Now, in reality, we have finite systems. So if we cut that system, we will expect to have a phase difference between these 2 points. That's acting like a phase battery if you want. So if I close a loop, something should flow there because of this spin galvanic effect. Right? So in other words, if now I take my superconductor, or let us not put even the name superconductor, material with spin galvanic effect, we apply the field in perpendicular to the current, and we close a loop. Let's say that we pass the current in that direction, or in that direction, we expect that the critical current parallel to the current, the critical current will be smaller than the opposite that one that needs to compensate first that current that to the spin galvanic effect. And that, in that respect, this is kind of a hand-waving way of seeing, okay, we have a diode effect, we understand this diode effect. But then we can also understand the finite effect, the finite junctions we saw today in the talk of Christoph, which are 2 superconductors grown on top of a system which was, in their case, was the 2-dimensional electron gas with strong spin-orbit coupling, again a Rashba system. And again, we apply the field just in the plane perpendicular to the screen. Yeah? So we get a currents flow so that if we close here now our loop here, we expect and we measure the current phase relation, we will see that our current phase relation has a shift in phase, which is this phi naught. So what I want here to summarize in this picture is that phi naught junction is nothing a consequence of the spin galvanic effect that, as we understand, I think, from the previous discussion. So to summarize this part, let me just, this is the message of the first part, non-technical part, just that magnetoelectric effects, spin galvanic effects in particular, finite junctions and superconducting effects are all one and the same thing. So spin galvanic effects behind these effects, if we talk about, in that case, only Rashba. Question is, only the Rashba superconductors will show that. Yeah? And does disorder affect that? Because in some devices, we should have disorder and so on. And this is the questions that we want to understand next. So now comes only, I promise, only 3 slides, a bit of formalism. So first question we had is, can we build such a nice phenomenological theory just from symmetry considerations? Have a general transport theory for this type of effects, valid to all temperatures. Let us remind what we have now in superconductivity, Ginzburg-Landau free energy, beautiful theory. We can start writing here terms, allowed per symmetry. And one of them is the famous Lifshitz invariant term, which is a term which is linear in the gradient. Yeah? And then you see here this Kij, this is a magnetic field, and Kij, again, has to be B, magnetic field is a pseudo vector, it is a second rank pseudo tensor. So, So if you want to have this term was written by many people, and turns out that this term gives us what they call anomalous current, which is nothing but spin galvanic effects in superconductors. So, spontaneous current in your superconductors. When we try to build something like that, but now valid for all temperatures, and not only in the superconducting states, also just above TC. And the answer is yes, of course, because this to talk about, and this is some archive this week. We can do it, and of course we cannot write Gizmo-Landau. Gizmo-Landau is valid for superconductors and close to DC. So what we have to go down is something more sophisticated, which is the nonlinear sigma model, which sounds kind of boof. Why should we go to that? But it turns out that it's beautiful. I was a student of Konstantin Efetov, and I always refused to do nonlinear sigma model problems. Now, yeah, he unfortunately passed away. Now I go back to my roots and say, why not? And the nonlinear sigma model, just very short, is an effective quantum field theory for the slow fields, which are this Q. And what is interesting is that the expectation value of this Q, of this slow varying field, is nothing but the quasi-classical Green function. So if we can construct such an action, we minimize this action, we will get a famous equation, which is called the Söderl equation, or in the normal case, the diffusion equation, with all the ingredients we want to have, spin orbit, and all the effects that, let's see what we discovered, just based on symmetry. And the work of Tim consisted in see that there are two fundamental symmetries in this nonlinear sigma model, which is the charge conjugation and time ordering. And if just in addition you put the symmetry of your crystal, for example, you have a set of constraints to build this. This is the typical nonlinear sigma model for a diffusion system. This is the diffusion coefficient. Here there's some time derivatives, superconductivity. Here is some Zeeman field. And then we can start adding terms and terms and terms, which should be scalars, and with these constraints, that with these two symmetries and the symmetries, of course, of the system. So this is what we have done, and we consider as an example the spin-orbit coupling. Spin-orbit coupling means I can add Pauli matrices, these are spins, and some gradients of this field. And we thought this, we start to play, and we just try to write all the terms which are our symmetries and constraints allowed for. And just make it very quick, just look only on the red titles. So we in the, sorry, this was too fast. Here, the second order terms, we get the spin precession, use spin-orbit coupling, very nice. This is the data-dust transistor type of term. And we get a spin relaxation, can be anything, can be anisotropic, isotropic, or else. If we go to third order, things start to become very interesting. Now we get our charge spin coupling terms, our magnetoelectric effects. Here we see the spin Hall term, right, which might be anisotropic, why not? Spin swapping term, another term which was predicted by Dyakonov, right? This appears also there. And here we got to the also third term, which is now contains, as you see, two Pauli matrices and one derivative. And this is the first one is the spin galvanic effect. And here we see this second rank pseudotensor gamma, okay, written like that. And another new term, which apparently is only correct some spin relaxation, which is this beta here that we have to explore it a bit more carefully. Until now we have the action, and so let us focus on that term. As I say, now we minimize our action, we get our equations. We can do, for example, what we in theory we love to do, it's linear response. And what we get is that the charge current, now the charge current has only one indexes, is coupled to the spin via a second rank pseudotensor. And you say, yes, so what? But this is amazing, because this spin, I haven't tell you anything about this. It was a superconductor, it was a normal metal, it was in equilibrium, it was non-equilibrium. I haven't say anything, because it's valid for, it's universal. So this coefficient here from your material, we will see next how we determine this coefficient. This delta is here. You can generate, for example, our triplets from yesterday. The triplets that you just generate by proximity of a ferromagnet. Right? It's an equilibrium property. They will enter here, somehow, in this quantity. So you will create then these currents under any conditions if your system allows for this second rank pseudotensor. Good. Let's go microscopically. What are the materials? Okay, I don't know if you can see that. Okay, these are the non-centrosymmetric point groups. I take it from that journal. Okay, you know, there are 21 classes and 18 are gerotropic. So this, if we exclude these 3, all the rest, they can show spin galvanic effect. And there were some beautiful article by He and Lo in which they just make a list of known superconductors which belong to different point groups, and all these materials, they should show the spin galvanic effect, finite junctions, diode effect. They are all the same in the superconducting state. Okay, so there are a group here, which is this circle here, which are this one, which are the polar ones. So they have a polar axis. So for example, a Rashba type of system should be of this polar kind. There is other very interesting experiment by Stuart Parkin using, thanks to telluride, they have a polar vector in plane, meaning now they are allowed for diode effect vertically at junctions and not lateral junctions, as I show you. Yeah. Because it belongs to one of these groups, so the polar group of non-centrosymmetric materials. So, but girotropy is more than microscopic. These were just microscopic properties of our system that manifest somehow on transport. Girotropy is also a 2-deg with a polar axis, let's say a mesoscopic scale, but it's also the squid we have seen also in Christoph's talk. When the squid is asymmetric, we also have our polar axis. You can see you see the symmetry of the squid is somehow broken in one direction. So that is why we have also in that case, in that device, we can talk about macroscopic girotropy. So it's not a surprise that you would observe this effect in so many systems. No? You apply a magnetic field, you break time reversal, you have some asymmetry in your system, and then, okay, I think this is even, the list of Christoph with much more papers here, just put some of them. The last talk was this one, that in principle, even if your sample is asymmetric, you should get that effect here. I think this was one important point, was not maybe explained in detail, that the asymmetry of the layer actually plays an important. Okay, so let me then try to show you that even if the system has microscopically the materials are centrosymmetric, like platinum, let's say a heavy metal like platinum, and we build such a junction, we will get the spin galvanic effect or the finite junction. And this work actually also done by Tim and the group, it was inspired in some, motivated by this experiment in Stuart Parkin group, in which they used the typical combination of platinum, YIG, and 2 superconductors on top. So, very short, we write our equations. Here's our action. We have just only isotropic spin Hall effect because it's platinum. Yeah? We put some isotropic relaxation. We put some diffusion there, right? And then we have some boundary conditions, some action for the boundary with the superconductor, which describe how superconductor correlations penetrates into the platinum. And then we have this nice interface between the platinum, or let's say the metal, and the ferromagnetic insulator described by the typical. So all terms, by the way, you can also only from symmetry arguments write these 3 terms in your interface if you have a magnetic moment, and each of these terms can be associated to this very famous spin mixing conductance terms derived by BERGERET and collaborators long time ago. So in other words, we have, I think, platinum YIG, hundreds of papers. We know exactly the numbers for this, or at least if we trust experimentalists. So what we built here was just we studied the finite effect, because we know that we studied the finite effect as a function of GI, which is the imaginary part of the spin mixing conductance, and GR. So, and if we plug the values for YIG, we're at here. So nothing. Yeah. If we, for example, take European sulfide, there are other experiments with European sulfide, which is a ferromagnet, then we have the hope to have a nice final. So what is going on? We ask ourselves. So that, for us, either, okay, there's a problem with the experiment, or there are some other effects at this interface that we are missing. For example, what they claim in that paper, that is kind of interfacial spin-orbit coupling, enhanced. But if so, this should also manifest in the normal state. The theory is valid from superconductor to the normal state. So what we propose is that why not to do the same experiment above TC, extract the interfacial parameters, then going down to TC and measure again this phi naught or Dyer effect and check if these two parameters, according to theory, should be one and the same. Okay, then the conclusion is, I hope I just convinced you there is a general theory that can put everything together. So spin galvanic effects as magnetoelectric effects in spintronics connected to the superconducting world. And technically, we did it at the level of nonlinear sigma model. But of course, now we need microscopic models to understand each of these terms. For the spin-orbit coupling, we have plenty of them. We have the Rashba models. Yeah? But as you have seen, there are new tensors there that can be probably related to some microscopic properties of your system. So then I show you that the lateral Josephson junctions we can build a field-free superconducting diode. There was no field there. All what we need is a ferromagnetic insulator, but it will work for a ferromagnetic insulator and probably not for YIG. So what we propose is why not to make an experiment with YIG platinum, right? Superconductors, and measure that above and below TC. So with this, I thank you for your attention.